Hello viewers, today in this program I will explain you about the convergence of sequence and series. Firstly, I will define the sequence as a sequence is an ordered set of real numbers a1, a2 dash 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 an. These real numbers are elements of the sequence. If the number of elements is infinite, then the sequence is said to be an infinite sequence and it is represented as this one. Now, I define the series. If a1, a2, a3, an be an infinite sequence of real numbers, then a1 plus a2 plus a3 plus and so on an is called a series. It is represented by sigma an. Now, I will explain you the convergence of the series. First, we define the convergence, divergence and oscillatory type of series. Convergent series: if sum of n terms of Sn tends to a finite limit as n approaches infinity, then the series is called convergent series. If sum of n terms Sn tends to either plus infinity or minus infinity as n approaches infinity, then the series is divergent series. A series which is neither convergent nor divergent is called oscillatory series. Now, I give the examples of various type of series. The first one is r plus r square plus r cube and so on, where r is less than 1. It is convergent series as it is a geometric progression with r less than 1. Second one is also convergent series in which we have 1 plus 1 upon 1 plus 1 upon 1 into 2 plus 1 upon 1 into 2 into 3 and so on. It is a convergent series. The third one is divergent series. Here the first term is 1 upon root 1, second term is 1 upon root 2 and so on. So, it is divergent series. And the fourth one is with alternative sign. First term is positive, second term is negative, then positive, then negative. It is oscillatory series. Some properties of convergent series are as follows. If a1, a2, a3 converges to limit L1 and b1, b2, b3 dash 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 converges to limit L2 are two series, then lambda a1 plus lambda a2 plus lambda a3 is also converges to lambda L1 and a1 plus b1 plus a2 plus b2 plus a3 plus b3 and so on converges to L1 plus L2. Also, the limit n tend to infinity, an becomes 0. These are the three properties of convergent series. Now, I will explain the test of convergence of various series. Since there do not exist any exact formulae for partial sums, different tests and theorems have been developed to help us for the test of convergence of the series. Some important tests for convergence are comparison test, Cauchy integral test, D'Alembert ratio test, Cauchy nth root test, Rape test, logarithmic test, De Morgan and Bertrand test. Now, I will explain you with example these tests. First, comparison test. Suppose sigma an and sigma bn are two series with positive terms such that sigma bn is convergent and an is less than equal to bn for every positive integer n. then sigma an is also convergent. For example, test the convergence of the series sigma n plus 1 upon n into 3 to the power n plus 1. Solution: for n greater than equal to 1, n plus 1 upon n into 3 n plus 1 is equal to 1 upon 3 to the power n multiplied by n plus 1 upon 3 n, which is less than 1 upon 3 to the power n. But 1 upon 3 to the power n is geometric series with common ratio 1 upon 3. It is convergent. Hence, by comparison test, the given series is also convergent. Second test, Cauchy integral test. Suppose nth term of series is fn for n is equal to 1, 2, 3 and so on, where fx is positive and decreases as x increases, then the series sigma fn converges or diverges according to whether the integral minus 1 to infinity fx dx is finite or infinite respectively. Example: test the convergence of series sigma n plus 1 upon n to the power p. Solution: the nth term of the series is fn is equal to n plus 1 upon np. Integral 1 to infinity fx dx is equal to integral 1 to infinity x plus 1 upon x to the power p dx. This is equal to integral 1 to infinity 1 upon x to the power p minus 1 plus 1 upon x to the power p dx. This is equal to integral 1 to infinity 1 upon x to the power p dx plus integral 1 to infinity 1 upon x to the power p minus 1. If p is not equal to 1, we get integral 1 to infinity 1 upon x to the power p dx is equal to x to the power 1 minus p upon 1 minus p from 1 to infinity, which is equal to 1 upon p minus 1 for p greater than 1 and infinity for p less than 1. Also, if p is equal to 1, integral 1 to infinity 1 upon x to the power p dx is equal to log x from 1 to infinity, that is equal to infinity. Combining the above two result, we have integral 1 to infinity 1 upon x to the power p dx is equal to 1 upon p minus 1 for p greater than 1 and infinity for p less than equal to 1. Also, from 1 to infinity 1 upon x to the power p minus 1 dx becomes 1 upon p minus 2 for p greater than 2 and infinity for p less than equal to 2. Therefore, we find integral 1 to infinity fx dx is equal to integral 1 to infinity x plus 1 upon x to the power p dx is equal to 1 upon p minus 1 plus 1 upon p minus 2 for p greater than 2 and infinity for p less than equal to 2. Hence, by the integral test, the given series converges if p greater than 2 and diverges if p less than equal to 2. Now, I will explain the third test, that is D'Alembert ratio test. For the series sigma an with an not equal to 0 for n natural numbers, limit n tend to infinity, a n plus 1 upon a n is equal to lambda, the finite value. If lambda is finite real number, then if lambda less than 1, series is converges. If lambda greater than 1, series is diverges. Example for this test is the test of convergence of the series sigma n upon 3 to the power n plus 1. The solution: the nth term of this series is an is equal to n upon 3 to the power n plus 1. limit n tend to infinity, a n plus 1 upon a n becomes limit n tend to infinity n plus 1 upon 3 to the power n plus 2 divided by n upon 3 to the power n plus 1, that is equal to limit n tend to infinity n plus 1 upon 3 n, that is equal to 1 upon 3, which is less than 1. Since the limit is less than 1, the series is convergent. Next test is Cauchy root test. For a series sigma a n of positive terms, limit n tend to infinity, a n to the power 1 upon n is finite value lambda. Lambda is finite real number, then if lambda is less than 1, series is convergent. Lambda is greater than 1, series is divergent. Example to test the convergence of the series from this test is, the example is sigma 5n minus 6 upon 3n plus 5 to the power 4n. The solution, the nth term of the series is an is equal to 5n minus 6 upon 3n plus 5 to the power 4n. Limit n tend to infinity, a n to the power 1 upon n is limit n tend to infinity 5n minus 6 upon 3n plus 5 to whole power 4n divided by n, that is 5 upon 3 to the power 4, which is always greater than 1. Since the limit exists and it is greater than 1, the series is divergent. Next test of convergence is Rabe's test. For a series sigma a n of positive terms, limit n tend to infinity, n multiplied by 1 minus a n plus 1 upon a n is equal to lambda, that is the finite real number. Then series is convergent if lambda greater than 1 and series is divergent if lambda less than 1. I will explain the test by taking the example. Here the example to test the convergence of series sigma 1 3 5 dash 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 2n minus 1, all terms, all odd numbers are in multiplication, divided by 2 4 6 dash 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 2n, all even numbers in multiplication. The solution of this test is, the nth term of the series is a n is equal to 135 dash 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 2n minus 1 upon 246 dash 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 2n. Then limit n tend to infinity, n multiplied by a n plus 1 upon a n is equal to limit n tend to infinity n upon 2n plus 2, that is equal to 1 upon 2, which is less than 1. Since the limit exists and it is less than 1, the series is divergent. Next test is logarithmic test. For the series sigma a n of positive term, limit n tend to infinity, n log a n upon a n plus 1 is equal to lambda, the finite real number, then the series is convergent if lambda is greater than 1 and the series is divergent if lambda is less than 1. The example to explain the logarithmic test, the test the convergent of the series sigma n to the power n minus 1 into x to the power n minus 1 upon factorial n. Solution, the nth term of the series is a n is equal to n to the power n minus 1 x to the power n minus 1 upon factorial n. Now, we will test the series by taking x is equal to 1 upon e. We find n log a n upon a n plus 1 is equal to n log e upon 1 plus 1 upon n to the power n minus 1, that is equal to n log e minus n minus 1 log of 1 plus 1 upon n, that is equal to n into 1 minus n minus 1 upon n minus 1 upon 2 to the power n square and so on, that is equal to the limit n tend to infinity n multiplied by n log a n upon a n plus 1 is equal to 3 by 2, which is greater than 1. Since the limit is exist and greater than 1, the series is convergent. Now, the next test for the convergent of the series is De Morgan's and Bertrand test. For a series sigma a n of positive term, limit n tend to infinity, n multiplied by a n upon a n plus 1 minus 1 whole minus 1 multiplied by log n is equal to lambda, the finite real number. Then if lambda is greater than 1, the series is convergent, and if lambda is less than 1, series is divergent. Next test is for alternating series. This is Leibniz test for alternating series, a series in which the terms are with positive and negative sign. The alternating series is a1 minus a2 plus a3 and so on. It is converges if each term is numerically less than the preceding term. A n is greater than a n plus 1 for every n, and limit n tend to infinity, a n is equal to 0. Now, I will explain the absolute and conditional convergence of a series. A series a n with positive or negative term is said to be absolutely convergent if a n and modulus value of a n both are convergent. If a n is convergent but modulus value of a n is not convergent, then a n is called conditional convergent series. Today in this program, I have taught about sequence, series and their convergence. To distinguish between series and sequence, the definition of sequence and series was given. To test the convergence of series, we have discussed various tests with example, namely comparison test, Cauchy ratio test, D'Alembert test, Cauchy nth root test, Rabe test, logarithmic test and De Morgan's test. Some special deductions of the test have also been discussed. Thank you. Hope you have enjoyed the lecture.